Hey, BC Calc, these are your day 87 notes. Today, it's kind of an exciting day. We get to learn some more derivatives for the first time. They're going to be the derivatives of some inverse trig functions that we know and love. The first page of our notes is, of course, some review. And I feel like typically I would say at this point, all right, try these before I see you next time. But in this case, I'll give you some time in class to work on these. So if you want to try them, of course, it's up to you. But I will afford you some time in class next time I see you to work on these 3 questions, including a former AP question from bringing it on back to the good old 1970s, a long time ago. All right, so hang on to those. Let's go on to the next page where in order to learn about the derivatives of inverse trig, we probably would benefit from reviewing some key points that relate to inverse trig. So for example, we use inverse trig to find angles in right triangles, right? So if I have this angle theta here and I want to find the measure of angle theta, we'd set up the appropriate SOHCAHTOA ratio using our right triangle trig. So if we have opposite and adjacent, that would involve tangent of theta equaling 1/3. And then I think a lot of us at this point would just sort of default to saying, all right, to get theta alone, you're taking the tan inverse of both sides. So therefore theta is tan inverse of 1/3. And we can figure out what the measure of that angle is in degrees. Oh my gosh, degrees. This is the first time we're even talking about degrees in this class. I'll say that, type that in. I don't even want you to change the mode on your calculator because we're just doing radians for almost everything here. But theta would be approximately 18 degrees using that tan inverse calculation. All right, in the next example, find the inverse of f of x equals cosine x. Well, I mean, really quickly, if we start with y equals cosine x, we'll just switch x and y. And then we know that if we're looking to get y alone, the only way to undo cosine of y here would be to take the cos inverse of both sides, which is what I described over here. I didn't actually write it down just to kind of save myself some space here. But if you write that down, I would say we typically just accept that we have this function, cos inverse that undoes the cosine function, but cos inverse of cos on this side is y, and then y equals cos inverse of x is an important enough function that we have a special notation for it. So, keep in mind that when I input values of x there to cos inverse, we're inputting angles is what we're really inputting there. We're inputting ratios, and that the output would be an angle, because usually we're inputting an angle for cos, and the output is a ratio. So we're doing kind of the reverse when we evaluate with cos inverse. And then finally, something like sine x equals 1/2. If I say to solve, here's a case where you can actually set up the scenario that we have 2 quadrants of answers, just initially from 0 to 2 pi. So I don't know what phrases you've learned in the past 2 years to remember where sine, cos, and tan are positive and negative. But certainly if you ever have had me, you would learn that you are in an all-star trig class. Okay, so all-star trig class would tell me that all the functions are positive in 1, and we're looking at positive 1/2. And that sine is positive in quadrant 2. So we're going to label the opposite and hypotenuses accordingly. Here's the angle x that we're looking for in question. We know that the adjacent side that's missing is radical 3. So the first solution is whatever the reference angle is across from that 1, which in degrees is 30, but we're not going to really use degrees too much. So let's call that pi over 6. And then if you're in quadrant 2, the other location where sine is positive, halfway around is pi, which is 6 pi over 6. So if that reference is pi over 6, take the half circle, 6 pi over 6, and subtract that pi over 6 out. The other answer just from 0 to 2 pi initially would be 5 pi over 6. If we somehow wanted to represent the solutions over the entire domain of the function, we would then add on the period of 2 pi, and we would attach an extra parameter n next to it, where n is some integer. So if we would add on 2 pi and add on 2 pi, or subtract 2 pi's, we'd get to an infinite number of answers that technically would satisfy the equation sine x equals 1/2. Good little trig recap there, especially as it relates to trig inverse. What I think will really benefit us is to think about what do the graphs of the inverse trig functions look like, and then therefore we'll be able to make some connections with what the derivatives of these inverse trig functions are. So if you want to take a moment here to see if you can recall what these graphs look like, I am going to show you based off of cutting up the sine, cos, and tan curves, what these three will look like. As a reminder, why do I have to cut up the sine, cos, and tan curves? Well, none of these are one-to-one functions. So we want to kind of grab the part of the graph that is one-to-one, such that when I switch the x and the y values, we get something that's going to still be one-to-one when I sketch it over here. Okay, so instead of graphing the relation arc sine and arc cos, we're graphing those as functions here. And if you think you want to hit pause and then kind of join up with me in a moment here when I show you the correct sketches, here's what you should have for arc sine of x, which is of course the same thing as sine inverse. So perhaps what you recall is that if you cut up the sine curve from negative pi over 2 to positive pi over 2, take these x, y coordinate points and switch them, you're going to get this resulting graph over here, and notice how the range of -1 to 1 is now the domain of this function. The domain of negative pi over 2 to positive pi over 2 is now the range of arc sine of x, which makes sense to me when we switch x and y. Okay, so beyond there, if we wanted to look at cosine of x and therefore arc cos of x, the interval that you should have cut the cos x graph up over is from 0 to pi. And if you take those, really maybe just these three key points, right? 0, 1 would become 1, 0. Pi over 2, 0 is 0 pi over 2. Pi comma -1 is -1 pi. And that's a quick way to generate the graph of arc cosine of x. Last but not least, tangent's a little interesting just because we have, those vertical asymptotes at negative and positive pi over 2. So those switch over to horizontal asymptotes on arc tan. The other interesting thing about tan, of course, is that we have a range of all real numbers here, so then that becomes the domain of arc tan of x, would be all real numbers. So when we look at the derivatives, I'm going to first just present what the derivative is, and then we'll talk about maybe some instances as to why it makes sense based on maybe what we know about the graphs of these functions. And then I'll algebraically show you why the derivative is what it is. So if we take a look at the next page, we have at the top the derivative of tan inverse of x is, big moment for us here, it's 1 over 1 plus x squared, of course. Well, it doesn't quite make sense yet why that's the case, but why does it initially make sense even just a little bit, thinking about what the graph of tan inverse looks like? Well, this expression 1 over 1 plus x squared is always positive, right? No matter what I plug in for x, that's always a positive expression. And tan inverse is always increasing. So it makes sense to me that the only way to evaluate the derivative here is going to have positive outputs, which we know that implies that the original function is always increasing. That's just an initial look at it to say, this makes sense to a certain extent just to get started, but why is the derivative of tan inverse 1 over 1 plus x squared? Well, if we start with y equals tan inverse, what I'm going to do is take the tangent of both sides. So on this side, tan of tan inverse of x. Because if you take the tan of tan inverse, those will undo each other just to be left with x. So what we're left with is that tan of y is equal to x. That's going to be an important substitution that we think about later on, but if tan of y equals x, let's come over here and draw a quick picture. So if here's my angle y, tan we know is opposite over adjacent, so the opposite would be x, the adjacent would be 1. And with some quick Pythagorean theorem, we would get square root of 1 plus x squared. The wheels are starting to turn because there's a 1 plus x squared in the derivative. All right, well, let's take a derivative, see what happens. Derivative of tan is sec squared. And then with respect to x, oops, we got to do that. This would be with some implicit differentiation times dy dx. And then the derivative of x is just 1. So therefore, dy dx would be 1 over secant squared of y, which doesn't quite look like what we have right here. So you have a few options as to how we can replace this. Well, first of all, you can evaluate what secant of y is. It would be hypotenuse over adjacent. And then we're going to square that, and oh, okay, that's going to leave me with what we have here. Or, remembering that tan of y is equal to x, we can replace secant with the Pythagorean identity that secant is 1 plus tan squared. And if tan of y equals x, then tan squared is going to be x squared. So therefore, we can prove here that the derivative, after taking the tangent of both sides, differentiate both sides, we can prove that the derivative is in fact 1 over 1 plus x squared. And then, of course, we always do this additional step when we define a new derivative, that if we have the derivative of tan inverse of u, where u is a differentiable function of x, then we get 1 over 1 plus u squared times du dx. All right, so let's just do these quick practice problems then. The derivative of tan inverse of 5x is going to be 1 over 1 plus the quantity, 5x squared. Okay, so u is 5x in this case. Make sure that you square that quantity, times the derivative of what's on the inside here. So du dx would just be 5. And therefore, your final answer would be 5 over 1 plus 25x squared. Okay. We can just as quickly and easily hopefully find the derivative of tan inverse of sine x. So we know that it's going to be on the bottom 1 plus sine squared. But then the du dx part would be the derivative of sine x, which is cosine x. So cos x is going to wind up being on the top over 1 plus sine squared, and that becomes our derivative of tan inverse of sine x. All right, well, moving on from here. Let's talk about the derivative of sine inverse then. Well, sine inverse's derivative is 1 over the square root of 1 minus x squared. Why does this initially make sense? Well, no matter what I plug in for x, I know that this is also always going to have to return a positive quantity. And sine inverse, if we think about the graph of sine inverse, this little one right here, is always increasing. So that's good. The other thing that we know about this expression right here is that it's only defined from -1 to 1, according to the domain of that denominator, radical 1 minus x squared. Oh wait, sine inverse also only define continuous on the closed interval -1 to 1, but if we're talking about a derivative, it makes sense. It's defined on that open interval from -1 to 1. And I bet you can justify why using a really similar derivation technique to what we just did with tan inverse. So if y equals sine inverse of x, sine both sides. Okay, if you even want to try it on your own, of course, you may feel free to do that. So then we get sine of y equals x, and then we're going to take the derivative of both sides. So this would be cosine y dy dx equals 1. So dy dx equals 1 over cosine of y. Now, I didn't define yet what sine of y equals x look like. If that's true, that sine of y is equal to x, we know that the opposite is x, and that the hypotenuse is 1. Well, if I do Pythagorean theorem here, just be careful that because we know the hypotenuse this time, this would be the square root of 1 minus x squared is what's left on the adjacent side. Oh, well, cosine's adjacent over hypotenuse, right? So this over the hypotenuse would just be radical 1 minus x squared, thus proving that the derivative of sine inverse is 1 over radical 1 minus x squared. Okay, so we actually get to that conclusion pretty quickly, especially since we've already done a very similar derivation with tan. Okay, so with respect, if we have a u in there, that chain rule step, it's going to be 1 over radical 1 minus u squared du dx. So if I find the derivative of sine inverse of 2x minus 3, it's going to be 1 over the square root of 1 minus, here's my u, so it's that quantity squared times the derivative of this inside part. The derivative of the inside part is 2, and the reason why I'm just kind of talking that out initially, because you can probably get right to the end step of just putting a 2 up in the numerator. It's the derivative of the inside, and then the square root of 1 minus the quantity 2x minus 3 squared. Okay, and we can stop there. You don't necessarily have to simplify any further as far as expanding or simplifying what's under the radical there. And then similarly for sine inverse of e to the x, it would be 1 over the square root of 1 minus e to the x squared times the derivative of e to the x, which of course is e to the x. So I'm going to put that on top. Square root of 1 minus, if you square e to the x, of course that could be commonly written as e to the 2x. Power to power, we'd multiply there. So something of that form is a good way to express the derivative of sine inverse e to the x. And then last but not least, well, if we have the going forwards with finding derivatives, let's go a little bit backwards. All right, so we have some good antiderivative practice here. And if we have the derivative of dx over 1 plus x squared, hopefully we're jumping back to thinking that this is tan inverse of x plus c. And then similarly, dx over radical 1 minus x squared, that's the pattern for sine inverse of x plus c. Okay. Now, it's really important that when you're doing this process that this is some quantity squared, and the same thing here, that this is some quantity squared. So if we look at these two examples, I'm looking at number 1, and I'm thinking that it's going to be very closely modeled to what we have over here with radical 1 minus x squared. But with that quantity 4x squared, we want to think about what am I going to let u equal? So what inside quantity squared would become 4x squared is really the question. So if I rewrite this, I want to write it as the square root of 1 minus something squared. That would be equivalent to the quantity 4x squared. Well, just really quickly take the square root of that, right? That would be 2x. And 2x quantity squared, of course, is 4x squared. So if u is equal to that inside piece, 2x, then du is 2dx. And now that I have that, I can multiply by a half. So we keep things balanced here. It's going to be half of du over radical 1 minus u squared. So we need that u substitution here such that we can then take the antiderivative. This is going to be sine inverse of u. So the final answer would be with the 1/2 out front, sine inverse of u, and I'll just in my head really quickly remember, oh yeah, u is 2x. So it's going to be sine inverse of 2x and indefinite, so we need our plus c there. So there's what we have for number 1. Okay. Number 2, kind of a similar feel where I have 1 plus 3x squared down here. But I want to think about what quantity squared can I rewrite this as such that we can relate it to the tan inverse antiderivative. So we're going to quickly switch this over here on this side to do dx over 1 plus. Well, again, you got to kind of like take the square root of this and think of that quantity squared. So the square root of this would be radical 3x squared. Okay. So if u in this example is radical 3x, then du is going to be radical 3 dx. So to create our balance here with du on the inside, we're going to multiply the outside of the integral by 1 over radical 3 this time. And du would now be over 1 plus u squared. Once we get it down to this stage, we know that that's tan inverse, so we get 1 over radical 3 tan inverse of u, where u is really radical 3x, and then plus c. And eventually, in a few days, we'll really justify and generalize this pattern for how we can get if it's something of the form minus 4x squared on the inside or the plus 3x squared. If there's another coefficient out front there, we'll be able to generalize a pattern that would get us to these antiderivatives, even maybe a little bit faster than using u sub. Although, of course, u sub is always a great go-to if we're unsure what to do there. I'll save number 3 for class tomorrow. If you're interested in giving it a shot, you could do it at this point, but the only thing I'll caution you about is that 4 there, okay? So we have to do something with that 4 because if we're thinking this relates somehow to sine inverse, well, sine inverse is only for 1 minus a quantity squared, not 4 minus. So we're going to have to do a little bit of work in advance there. That's my big hint for number 3. And number 3 is also a definite integral, so we'll be able to plug in those bounds eventually too. All right, that is it for day 87. Some great new trig derivatives. Let me know if you have questions next time we're in class.